We're going to start with the notes that I've given to you. The other sheet is a practice sheet. So this one over here that you got, the one that says discrete random skill sheet. Solutions are just in OneNote, just below. So if you go all the way down, you'll find the solutions on OneNote. Again, this is on exercise 11 ABC. Find that page and you'll be able to find the skill sheet and the notes. Okay. Here we go. Let's go through the notes. So 2 things that you need to know. What is discrete random variable distribution versus binomial? Okay, they're really fancy names, but really if I had to summarize it, it's just learning how to read a table of probabilities. That's skill number 1, which we can talk about discrete. And skill number 2 is with replacement formula. So you have done questions that are with replacement back in year 7, 8, and a bit in 10. We're now looking at a formula for it, and there's a special name for it. It's called binomial. And those are the only 2 things that we're really looking at. Okay, so what are you going to take out? How to use a CAS calculator to do the formula bit. And this part here is just reading notation. So you're just getting familiar with reading a table and reading notation. For a lot of students, it's the notation that seems to throw them off to start off. But let's go through some notes. So there's only 2 goals to work on. When we say discrete random variable, so the question is, what does random variable mean? It means that it has a value determined by the outcomes of an experiment. Okay, so when you do an experiment like flipping a coin, rolling a dice, that's called an experiment or trial. And the outcomes that you get, it's random. So the results for it, it's random, so we call it a random variable. These random variables are expressed as an uppercase letter, meaning capital letter, and the values that they can possibly take are expressed as lowercase. So that line there, I'm going to highlight again. This is where students get a bit confused. So I'm going to show you what it looks like, so then you can then make sense out of it. Capital letters represent what you're actually looking at. Lower letters represent, well, what is it going to equal to? So here's an example. If you roll a 6-sided dice 5 times, right? And then I use a capital letter. So you notice I'm using a capital letter. I say, let X be the number of times a 3 comes up. So think about a dice. Here's your dice. I'm going to roll it 5 times. And I'm saying, out of those 5 times, so 1, 2, 3, 4, 5, I'm interested in finding how many times I'm going to get a 3. Okay? But I use the capital letter X and how many times I'm going to see a 3. Now, if I roll it 5 times, this is one possibility. I could get a 3 on the first go. Don't get a 3 on the second go. Get a 3 on the third go. Don't get a 3. Don't get a 3. So in this case, how many 3s? How many 3s did I actually get? 2. So in this case, I would say capital X, little x equals 2. Does that make sense? See, capital X represents what is my random variable. My random variable is I'm interested in the number of 3s. How many 3s did I get in this particular experiment? I got 2. So if I actually wrote this out, do you see why capital X is the number of times that the 3 comes up? But then you use a little x because it depends on, well, how many different 3s can you get? Well, you got 5 trials, or 5, it's one experiment, but 5 trials. What's the maximum number of 3s I can get? I can get all 3s. 1, 2, 3, 4, 5. So I could get 5 3s. That's why there's a 5 here. Or I may not have gotten any 3s at all. So my minimum be 0. So this now represents 0, 1, 2, 3, 4, 5. A very distinct data It's the data to represent how frequent or how many times of the thing that I was interested in, which is my random variable. Does that make sense so far? Okay, so the language we use is just that capital X and little x. For some reason, students get very confused by it. And this is where it happens. You know when we say discrete and continuous back in year 7, you have to determine is a data discrete or continuous. Remember, discrete is countable. Discrete means you can count it. So it doesn't go on forever, right? So discrete data can be counted. For example, number of siblings, your shoe size, you're either 10, 10 and a half, or 6, 6 and a half. It's very distinct. Postcodes are also distinct, right? Whereas continuous data can be, well, more like measured. There are infinitely many possibilities. For example, your height, you could be 1 meter and 70 centimeters, but you could have been 1 meter and 71 or 72, or maybe even you want to go even a bit further, you can actually change that. So it's not like discrete where it's very distinct. You're either 170, 180, 190, so it's only that. There's nothing in between it. So we like to think of continuous data as things that are measured. There's infinitely many possibilities in between, whereas discrete, it's very distinct. You only get 1 or 2. You can't get things in between. So you can only count, you either have 1 sibling, or you have 2 siblings, or you have none. But you can't have half a sibling. You can't have a third of a sibling. You can kind of, if you actually physically do it, cut them up. But does that make sense? Discrete. So we put those 3 words together. Discrete, random, variable. Have you noticed that the data that we use, or the one I'm using, let x be the number of times a 3 comes up? X is my random data, but that data that I have, 0, 1, 2, 3, 4, 5, is countable. It's not measured. Yeah? That then gives us a set of skills that we currently have to then analyze that. So what's the first bit to understand? This is all you need to understand. So I said you just need to read a table, right? Capital X represents, in this case, 0 getting out of 5 trials of 5 rolls, I get 0 threes, 1 3, 2 threes, 3 threes, 4 threes, or 5 threes. The next notation, this is where students get confused, and hopefully I've explained it well enough to you for you to understand this bit. PR, which means probability, bracket capital X equals little x. This is what students get confused about. And if you really think about what I'm saying there, this is saying your random variable x, how many does it equal to? Is it 0 threes, 1 3, 2 threes, 3 threes, 4 threes, or 5 threes? That's why it's a little x there. So for example, if you wanted to know what's the probability of getting 1 3 if you rolled 5 times, this probability right here is the same thing as saying probability of capital X equals 1. Because you're saying, I want number of threes. How many want? I want 1 of them. This represents 2 threes, 3 threes, 4 threes, 5 threes. But the notation here, that's what I'm saying. The capital X equals whatever little x is. Little x was either 0, 1, 2, 3, 4, 5. See what I'm saying there? So at year 12 level, that's often one of the first things I really try to get my 12s to understand. And often, the exams actually is coming up really soon. Often the students are behind. This is one of the first things they ask me. It's because they missed out on that session or they're not listening during that session. So when the first time they see this, they're like, what is that? And all it really is capital X is random variable. Little x represents, well, how many of those random variables are you interested in? So you got the 0, 1, 2, 3, 4, 5 in the example I gave you. So the example is roll a dice, roll it 5 times. What I'm interested in is number of threes. Number of threes is countable, so I can get 0 threes in 5 shots, 1 3 in 5 shots, 2 threes in 5 shots, all the way up to 5 threes in 5 shots. Yeah? So that little x there, it's what? 0, 1, 2, 3, 4, 5. So when you see that, don't get scared. It's really just saying chances of which one? Which one are you interested in? So, therefore, I can break this up. And you can write this. If you want to find the probability of getting all 3s, then this one would be x equals 5. Because I already said at the start, let x be the number of times you get a 3. So what I'm saying there is, I'm saying, what's the chances of getting 3s 5 times in my 5 rolls? That's what that's saying. Okay, so it's just learning notation. That's the first bit. All right. If you understood that, that was the first part of the skill that I wanted you to understand. It was to read a table of probabilities. This is called a probability distribution. That's the name for it. But let's do an example. Let's do an example just to tie everything I just said, because your goal is to be able to read this table. So eventually, you're not going to be given all of this. I'm not going to give you any of that. Your job is to be able to read a table and understand some of the restrictions. Okay? All right, let's guide you through. Let's start off with a new problem. Example 1. You got 2 coins. They're drawn from a bag, and the bag contains 2 white and 3 black coins with replacement. So let's draw a tree diagram. So you have 2 coins that are drawn. You're going to pick out 2 coins. So you draw out 2. So number trials is I'm drawing out 2. In my first draw, there's only 2 possibilities I can get. I can either get a white or a black coin. What's the chances of getting a white coin in this scenario? Can I please have, let's go with Adi. What's the chance of getting a white coin? 50, is it 50%? 2 whites out of 40%. Yes. 2 out of 5, 40%. And then therefore, black, new Muffy, what's the chance of getting black coins? 3 out of 5. Very good. So that's my first go. So I don't know what I'm getting for the first one, but that's at least what I know. I got a white or a black. But then, if I got a white, because it's with replacement, my coins go back into the bag. I still have 5 coins. Again, I have white or black as my option. What's the probability of getting white again now? Let's go with Lockie. Still 2 out of 5 because nothing's changed. So therefore, this is still 3 out of 5. And then if I did the second one, same idea, W, B, you still get 2 out of 5, 3 out of 5. So far, pretty straightforward. Yeah? What is now the next step to then bring it into pretty much year 11 content where you're reading the distribution table is you need to define what X is. So capital X is my random variable. What am I representing it? I'm representing it as the number of white coins. So now I know. It's not the black coins I'm interested in. I'm interested in the white coins. So how many white coins can you possibly get? Now, if you think about it logically, if you draw out twice, what's little x going to equal to? Because I know capital X is equal number of white coins. What's little x is? What's little x equal to? Let's go with Massey for this example. So, could be 0 or 1 or 2 because I'm only doing 2 trials, right? So I'm only picking out 1 or I'm picking out 2. So out of those 2, it's possible that I could have got black and black, so that means 0 whites. I could have got black and a white, so I get 1 white. Or I could get white and a white, so then I get 2 whites. That's the only 2 scenarios, but the key part was to understand the difference between writing capital X, so you're defining what you're interested in, and then what little x represents. Little x now represent, and notice that's discrete. Yeah, 0, 1, 2. You can't have 0.5, you can't have 0.1. That's why we call that discrete random variable. Does that make sense? Yeah? So then when we put it as a distribution, so let's have a look at the scenarios I could have got. We could have got outcomes. We're drawing 2 coins. You could have got white and a white. Then you could have got a white and a black. Or you could have got a black, then a white, or a black and a black. If we count the distribution, well, in this case, x is equal to, little x is equal to 2, little x equals to 1, little x equals to 1 again, in this case, little x equals 0. So when we put it into a distribution table, this is what you're going to be doing. You'll just be looking at that. Okay, we usually give you the distribution table, and you have to understand what that represents. Yeah, so little x, sorry, that should be capital X there. That should be 0, 1, or 2. Now that second row, again, reading that notation, that just means what's the chances of your random variable, which in this case, getting a y, is equal to little x. So little x is it 0, 1, or 2? So if I want the first one here, this is just saying that's the answer for this bit. That's why it's little x right there, because I don't know what little x could be. Little x could have been 0, it could have been 1, could have been 2. So I'm interested in finding what's the probability of having 0 whites. So out of 2 flips, 0 whites means that I have to get all black. That's the only way to calculate this one. But if you want to calculate that, black and black, isn't that just 3/5 times 3/5? So hence my answer, 3/5 times 3/5 gives you 9 out of 25. So the probability here is 9 out of 25. Okay? Let's do the next one. If I want 1, the only way to get 1 is white then black or black then white. So there's 2 scenarios there. You can either get 2/5 times 3/5 or, so plus 3/5 times 2/5. And that gives you, what, 6 over 25 times 2, so that's 12 out of 25. So now I know that's 12 over 25, yep. Because that's your random variable. This is the little x.
Aren't those little x's true? That big x doesn't little x represent like why is that big x?
Oh, yeah, that's true. Usually I see capital X's there, but now that you say it, maybe I saw wrong. Yeah, maybe it should be little x.
Little x is not big x.
Okay, then I was wrong here then, sorry. So little x was correct when I wrote up my notes. That's true. Capital X is the definition, and then little x is the way to go. That's right. And then the capital X is going back to discrete random variable equals little x. That's true. Thank you. And the last one, capital X is equal to 2. So that means the only way to get 2 whites is just white and white. So it should be 2/5 times 2/5. 4 out of 25. Now let's look at a couple of properties. So usually we don't give you the tree diagram. We also don't give you that little table that I've done over here. So you wouldn't get this table. And you usually will not get the calculations for that. All you get is the scenario, and then they give you this. Okay? Now let's look at this distribution table. So this is called, the name for this is called probability distribution table. Why is it called a probability distribution table? Because that means on your CAS, if you would type this on your spreadsheet, the x-axis now represents little x. So you got 0, 1, 2. And then the y-axis now represents probability. So you can actually visualize what the distribution looks like. And that's what you do next year. So next year, you get graphs of what the probability distribution looks like, and then you analyze from the graph, or you can analyze from the table. This year, you don't need that. You just need to understand how to read this table. Couple of basic ideas. If I add all the probabilities together, what should I get? 1. So that's one of the properties. So just below, can you see how it says 2 conditions? I know it looks nasty, but all it really is saying is if you add all the probabilities together, so that symbol, that Z looking symbol, that means sum all the probabilities for little x should equal to 1. What do you think the second property means? What does this mean? So P must be probability. It's the function for the picture of the distribution. What does it mean by probability function is between 0 and 1? What does that mean? All right. Let's go back to the table. What can't probability be? What can't it be? Can't be? Can't be a negative number. What does that mean when it can't be a negative number? It means that the graph, whatever distribution you get, no matter what it looks like, notice the function for it, if you had to create a function for it, it will always be above the x-axis. And so one of the things we say is let's call that p of x, whatever the function looks like, p of x. Clearly, you could have just said p of x greater than or equal to 0. So we're just saying that the function has to be above 0. But essentially, they're trying to say here that the max probability is only between 0 and 1. Okay, so those are my two conditions. Probability can't be negative, and therefore it can only be between 0 and 1 max. You can't have 101%, and you can't have negative 1%. Okay, so these two conditions here look scary, but really that's just makes sense. So most of you will be able to read the table and pick up on that. All right? All right, team. So that's the first skill. If that was easy, well done. If it wasn't, that's all you needed to know. Yeah, just read the table. All probabilities add up to 1, and we know the probabilities can't be negative. And just knowing how to read that notation, little x is the random variable, how many times you're interested in it occurring. Cool? Can I get a show of hands who feel like that kind of makes sense, at least the first page? Okay, cool. I've got about maybe a third of you. All right, there's about 70% of you who may need to watch this video again. All right, let's do an example. Let's see if you understand this. So here's a table. This is a distribution table. Which of these is a discrete probability function? I'm going to pause the video. All right, we're recording. Last bit for today. And pretty much that's the end of Unit 2. This is from the Year 12, it's Chapter 13. For you guys, it should be 11C. Okay. Binomial distribution is still a probability distribution. The only difference is this is when you have with replacement. So this only works if your tree diagram has the same probability for all of them. So, for example, 1 on 5, 1 on 5, 4 on 5, 4 on 5. Has to be that way for it to work. So, these are the conditions. I know there's a whole bunch of words here. All you need to focus on is this. For you to have a binomial, bi meaning two outcomes, you either get it or you don't. So binomial distribution relies on the fact that it's a Bernoulli sequence. What's a Bernoulli sequence? You only get 2 outcomes. Okay, so you either get it or you don't. So for example, you get tails or you don't. You get a 3 or you don't. You pick out a red marble or you don't. If you get that, that's condition number 1 of a Bernoulli sequence. So if you can get 1 out of 2 outcomes, so meaning there's only 2 outcomes, that's the first condition. Second condition, you have to have a probability of success that is constant. Meaning, with replacement. So that's an example. You either get it or you don't. You either get it or you don't. And each probability is the same. So what this constant means is with replacement. Can you write that down, please? Okay, so you got 2 outcomes. Has to be with replacement. And the third one needs to be that each trial that you do is independent. Now, you guys learned independence already. Independence means that each roll that you do or each coin flip that you do, it does not depend on what happened before. Usually they have to tell you. The question will tell you. So if you ever see a question that says if this is independent, as soon as you see the word independent, you should be thinking of binomial. So that's a big hint. Independent means not conditional. If you meet all three conditions, it's a Bernoulli sequence. If it's a Bernoulli sequence, you can have a binomial distribution. If any of those do not meet, you can't have a binomial distribution, meaning you can't use the formula I'm about to show you. Okay, so the formula only works if one, you have two possible outcomes. Two, all the probabilities have to be the same, meaning it's going to be a replacement. And three, they're all independent. Okay, so if I summarized it in 3 dot points, 2 outcomes, constant probability, and independent. That's pretty much what you need in order for you to use this rule that I'm about to give to you. Okay? Here's the rule. Thanks, team. Let's focus on the rule, and I'm going to go back to that example we just did before, so you can see how I'm going to use my CAS, and if you've got your CAS, we can practice it together so you can see how much faster it could be, and it could also, for larger problems, this formula becomes useful. This formula, I'm just going to copy that, and I'm going to bring it all the way back up to the very first page. Remember this example I did with you about the white ball and then, 2 coins that you take out, and you got whites. How many whites? 2 whites, 3 blacks, yeah? And you worked out these probabilities here. You can actually work this one out using binomial. Why? Because notice the tree diagram fits the conditions. You only got 2 outcomes. You either get white or you don't. And each probability is constant. And each trial is independent of each other. So you can keep picking out a bag, and it's always with replacement. So therefore you can use binomial. Yeah.
What would be a case where it would be with replacement, but not with...
Oh, that's a specific one. Because independent often you have to check if probability of A given B is equal to probability of A. That's true independence. So there are some scenarios, I just can't think of the numbers to make that not work. But there are numbers where you do replacements. But usually if you do replacements already, that's another word for it got to be independent. Because if you're replacing it, it means you're not changing the trials. If you're not changing the trials, it's all going to be the same. So replacement usually is synonymous with independence. But by definition, that there is the definition for independence. Yeah. So then you have to test to see if that's true or not. Yeah. All right. So in this scenario here, how could you have done this without doing the tree diagram and doing those little steps that I've shown you there? Grab out your CAS. Here we go. I'm going to show you how to do it. So for your exams, this is all you need to know how to do. If it does come up, you can go menu, probability, distributions. Take your time. I'm going to wait for you to get to this page. So instead of doing what we did before at the start of the session, you could have used binomial because it fits the 3 criterias. You go probability, distribution, and if you scroll down, there are 2 functions that you could be using for the exam. One's called PDF, one's called CDF. PDF is the one we're going to do as an example for now. PDF is for one instance. CDF is if you're adding them all together. So here we go. PDF. How many trials are we doing? We're doing 2 because we're picking 2 coins from the bag. So here's the example. Remember, I'm picking 2 coins. So N is 2. N is 2. Probability of success. Well, what am I actually looking for? I'm looking for the chances of getting white coins. Chances of getting white coins was 2/5 because you know there's 2 white coins in the bag. So probability of success, I'm just going to write it again. Here we go. binomial distribution has the rule nx p to the power of x, 1 minus p to the power of n minus x. I want to break it out again. N is the number of trials. P is the probability of getting what you want. And x is how many you're choosing. Or little x. I'll just write x equals random variable. So here we go. Probability of success, we said 2 whites out of 5 coins. And how many whites do I want? Well, let's see. So in this table here, if you wanted 0 whites, then x would be 0. See that? 0.36. And we got 9 out of 25 before. 0.36 as well. So same idea. So if you want to do it again, you can do it again. Binomial PDF, so I'll guide you again. Menu, probability, distribution, and the letter A is binomial PDF. So here we go, number of trials. So I had 2 trials. I'm picking out 2. I did 1 coin, then I did 2 coins. Probability of getting a white coin, I had 2/5. How many do I want? I wanted 1 white coin. 0.48. Let's see if it's correct. So I got 12 out of 25 over here. So let's see, 12 out of 25. 0.48 as well. So instead of doing it this way, instead of doing it through a tree diagram and getting to this point, I can actually get the answers straight off from the table. Okay? Why is this useful? Well, what if I did it 3 times or 4 times? What if I picked out 4 coins instead of 2 coins? You don't want to draw a tree diagram and you don't want to be doing this by hand. By using binomial, it's much more consistent because you know it's going to be white, black, white, black, white, black. Then the more trials you do, you can still calculate it. And that's why it's faster. But you can only use this rule. You can only use this rule if it's a Bernoulli sequence. Okay? Now this rule, why did you have to learn combinations for next year? Notice in the rule, this is combinations. So in my case before, when I was working out what's the probability of getting 1 white coin, and when you type on your calculator and you do this, how does it get 0.48? This is what they're doing. They're doing 2 trials, choose 1. So I want 1 white coin. What's the probability of getting a white coin? 2/5. How many are you going to get? I only want 1 of them. What's the chances of not getting a white coin? So this is white coin. This is not white coin. So that's the chance of getting black. That means 2 minus 1. So out of your 2 trials, you get 1 white, 1 black. That's why it's 2 minus 1. That's why you get 1 white, 1 black. So if you type this in your CAS, if you were to do it manually, this is what it looks like. Probability, combinations, choose 2, choose 1, multiply 2, 2/5 to the power of 1 times 3/5 to the power of 1, or 2 minus 1. That's what you're actually typing in manually. This is how many different ways can you have 1 white, 1 black, and that's why you times them together. So this is the chances of getting white, chance of getting black. Like I said, usually I go through the depths and show you where that formula comes from. In your case, you just need to know how to do that. Okay? This is more depth understanding. You just need to know when to use this. Okay? Next year, you'll be learning more of that. Okay? So where did this come from? Why do you need to know combinations? That was why in chapter 10, the only thing we focus on is combinations. All right? I'm going to probably stop there because I think that's a lot of info. And it's really huge on what I need to teach in just one session there. So what do you take out of it? 2 formulas. So one formula. One formula for you to understand, which is just this one here. That is binomial PDF. On the bottom part, I got CDF for you. when the question asks is something like x greater than or equal to 1, then you would have had to do something like find 1 white, 2 whites, and then 3 whites. Instead of doing PDF, 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 that's 3 times you have to do it. It's actually quicker to use CDF, and it'll do that for you. So you would just tell it to go from 1 to 3. So here's an example. Instead of doing this, instead of doing find the probability PDF for this one, PDF for this one, PDF for that one, and then add them together, what you can do is you can do 0 to 2. Now we know the answer should be 1. So let's try it. So instead of doing binomial PDF, 2 fifths, 0, plus binomial PDF, 2 fifths, 1, plus binomial PDF, 2 fifths, 2. See, I know the answer is going to be 1. You don't have to type all that in one go. You can do it all in one go. Go to menu, probability, distribution, CDF. So number trial is still the same. You got 2, probability of getting a white coin, 2 fifths. And then now we can say from 0 to 2. So then it will do PDF for 0, PDF for 1, PDF for 2, and you'll get the same answer. And that's just quicker. Okay, so that's the difference. And I already wrote the notes in your sheet in case you wanted to try it. That's what the CDF means. CDF is cumulative. And that's what CDF does. So it's when you're looking for greater than or equal to 1, instead of doing PDF 1, PDF 2, PDF 3, you can do 1, 2, 3. All right, thanks team. I'm going to stop the video there.